We present our work on improving controllable generation training convergence thanks to x0-Supervision. Over the past few years, significant progress has been made on text-to-image generation. However, no matter how good these models are, their reliance on natural language alone limits their practicality in scenarios where a specific layout of the scene is needed. Taking this image as an example, it can be quite difficult to describe this layout with pure language. Hence, language provides limited compositional descriptive power. This results in high inference costs because of many trials and prompt refinements in the hope of getting the desired layouts. Therefore, a bad user experience. As we say, an image is worth 1,000 words. The pioneering work of Zheng and colleagues introduced the idea of using additional spatial controls that better describes the scene to steer the generation towards the desired outputs. On the top, we have some examples of controls such as a depth map, a semantic segmentation, or a human pose. And at the bottom, we have some generated samples that follows these provided controls. A control diffusion model is built by plugging to a pre-trained text-to-image model a trainable adapter taking in the novel conditions. Then comes the question on how to train the control diffusion model. Basically, to train a diffusion model, we noise an input image to a certain level and ask the network to predict a value that can be used to retrieve the original image. In the literature, we either predict the noise, the clean image, or the velocity that is simply the time derivative of xt. Since we can easily convert one value to another, we can predict one value and supervise with another. This results in 9 configurations that can be used to train a diffusion model. Prior works systematically use the diagonal approach, highlighted here in red, to train the controlled model. That is, supervising an epsilon prediction model with the epsilon supervision loss, or a V prediction model with the V supervision loss. Although this is natural and effective, we rather propose to supervise any predictor with the clean image, that is the x0 supervision loss. Why? The key observation for our work is that all of these 9 configurations are equivalent to applying a certain weighting function highlighted here in red to the x0 supervision loss. So why is the weighting function so important? First of all, the weighting function has a clear impact on the training dynamics and the final performance of the diffusion model. Moreover, when we look at the sampling process of a diffusion model, it proceeds in a quartz-defined manner. In the quartz phase, the model tries to determine the rough layout of the scene, while in the second stage, it adds fine-grained details. When we supervise with other than the clean image, the weighting function tends to vanish near the noise distribution that is in the first phase. In a pure text-to-image setting, since the x0 supervision task is quite complex, because many layouts can satisfy the same prompts, this weighting pattern could make sense. In a control setting, however, we need an accurate prediction of the layouts, since later steps will only add fine-grained details. So using the same weighting pattern will no longer make sense, since it will prevent the model from learning to quickly pick the right layout. Based on these observations, we propose to supervise with the clean image. This has the effect of removing this poor weighting in the new noise region that is quite important in finding the right layout in a controlled setting. Here we show a visual example of the convergence dynamic with the baseline approach and our approach. In the case of semantic segmentation, we can see that when using x0-Supervision, ControlNet converges faster. Hence, we can see that the model quickly follows the rates, layouts, and the semantics of the objects. In the case of post-guided generation, again, we can see that the model quickly learns to follow the right human poses. To quantitatively measure the convergence speed, we propose to average the performance curve over multiple training time horizons. This averaging makes the metric less sensitive to a given time horizon, promotes initial cumulative gains, and reduces the effect of a performance plateau on the final metric. Here we show the quantitative results on spatially aligned controls. As we can see, x0-Supervision clearly improves all metrics on ControlNet and text-to-image adapter. On OmniControl, however, we observed that the baseline approach was already converging quite fast. Hence, x0-Supervision mainly maintained the same metrics on depth, semantic segmentation, and Kenny edge control. On post-guided generation, however, we observed a significant improvement of the convergence speed. Here we have the convergence curves. We can see a faster convergence and the sudden convergence phenomenon happening much earlier on ControlNet. In the case of non-spatially aligned controls, that is, those not specified in image form, the convergence speed is quite slow. x0-Supervision has a significant impact in this setting, as can be seen in the case of text grounding. We also have an improvement of the training convergence in the case of text and image grounding. Here are the convergence curves in this setting. Please find the code of this work following this QR code.